Welcome to you all in this course on fluid mechanics. In the last lecture, we discussed the orthogonal curvilinear coordinate system, some special kind of orthogonal curvilinear coordinate system. Particularly, we discussed the Cartesian coordinate system, cylindrical coordinate system, and spherical coordinate system. We find out the gradient of a scalar function and divergence and curl of a vector function in this system. So now in this lecture, we are going to discuss how to describe a motion in the fluid mechanics. Then we shall try to make the interrelation between those methods of describing the motion in fluid mechanics. So let us start. There are two ways to describe the fluid motion mathematically. So one is called the Lagrangian description or material description, and another is called the Eularian description or spatial description. So firstly, let us discuss what is a Lagrangian description. So in this method, we shall discuss the instantaneous change in the position of each particle. Its meaning is that suppose starting a particle is at x naught, y naught, z naught, and after time t, suppose t is equal to t naught, and suppose after time t its position changed to x naught, y naught, and z naught, then this position x naught, y naught, z naught will be the function of initial position x naught, y naught, z naught, and the time t by which this position has changed. So its meaning is that this position x naught, x, y, z will be the function of initial position x naught, y naught, z naught, and t. So therefore x is a function of initial position x naught, comma, y naught, comma, z naught, and t, and y will be also the function f2 of x naught, comma, y naught, comma, z naught, and t, and z will be also the function f3 of x naught, y naught, z naught, and t. Now suppose the velocity component in the Lagrangian description, it is given by u comma v comma w, and acceleration component in the Lagrangian description is given by ax, ay, and az. These components are along x, y, and z directions respectively. Then the velocity components u, v, w are expressed as u is equal to dou x by dou t, v is equal to dou y by dou t, and w is equal to dou z by dou t. And acceleration ax, ay, az are expressed as ax is equal to dou 2x by dou t square, and ay is equal to dou 2y by dou t square, and az is equal to dou z by dou t square. Now since x, y, z are the function of initial position x naught, y naught, z naught, and t, so this velocity components u, v, and w will be also the function of initial position x naught, y naught, z naught, and time t, and acceleration will be also the function of the initial position x naught, y naught, and z naught, and t in the Lagrangian description. So in Lagrangian description, so a quantity related to the fluid will be the function of the initial position x naught, y naught, z naught, and time t. Now we shall discuss the Eularian description. So in Eularian description, we fixed a point in the space occupied by the fluid and study the changes take place in the velocity, density, pressure, etc. Means the changes take place in the some fluid property as that fluid is passing through the point x, y, z. Now suppose u comma v comma w with the velocity component along x, y, and z directions at the point x comma y comma z at time any time t, then this velocity component u, v, and w will be the function of the space coordinate x comma y comma z and time t. So u I consider as function g1 of x comma y comma z comma t, v is equal to function g2 of x comma y comma z comma t, and w will be also a function g3 of x comma y comma z comma t. So u, v, w will be the function of space coordinate x comma y comma z and time t at which these changes take place. Now suppose we fix this time t. So for a particular time t, u, v, w this equation 4, what this equation will become g1x comma y comma z, and this t will be fixed. So equation 4 represents the velocity at the point in the fluid at that time. Okay, so we have fixed this time, so at that time it represents the fluid velocity. Now suppose we shall fix this point x, y, and x, y comma z. So this point we shall fix, then this fluid velocity will be the function of t, and this gives the modes of variation of velocity at that point. So what is the basic difference between these two descriptions? So in Lagrangian description, initial coordinates plays an important role. So in Lagrangian description, the quantity related to fluid will be the function of initial coordinate x comma y comma z comma t, while in the Eularian description, the point in the space by which the fluid particle or the changes take place, that's play an important role, and the quantity related to fluid will be the function of the space x comma x coordinate x comma y comma z and time t in which that changes takes place. So these are the basic difference between the Eularian and Lagrangian descriptions. Now we shall try to interrelate, means a quantity is suppose given in the Lagrangian description, what will be the same quantity in the Eularian description, and in the same way a quantity is given in the Eularian description, then what will be the same quantity in the Lagrangian description. So let us start. Firstly we are going to discuss Lagrangian to Eularian description. So suppose a motion is described in Lagrangian description by x is equal to function f1 of x naught comma y naught comma z naught and t. Y is function f2 of x naught comma y naught comma z naught comma t, and z is equal to function f3 of x naught comma y naught comma z naught comma t. So here you see these x, y, and z are the function of initial coordinate x comma y comma z, x naught comma y naught comma z naught and t. So this is the in the Lagrangian description. Now suppose phi be a quantity. So phi be a quantity in the Lagrangian description. So this phi must be the function of the initial position x naught, y naught, z naught, and t. So phi is given by equation number 6. Now what we shall do, we shall solve equation 5 for x naught, y naught, and z naught. So when we shall solve equation 5 for x naught comma y naught comma z naught, that solution for x naught comma y naught comma z naught will must be the function of x, y, z, and t. So suppose the solution of equation 5 for x naught comma y naught and z naught is given by equation 7, that is x naught is equal to g1 function g1 of x comma y comma z comma t, y naught is equal to function g2 of x comma y comma z comma t, and z naught will be the function g3 of the space coordinate x comma y comma z comma t. Now we obtained x naught, y naught, z naught. Now we shall put use equation 7 into equation 6. We replace this x naught, y naught, z naught with the help of x naught is equal to g1, y naught is equal to g2, and z naught is equal to g3. We shall obtain phi is equal to phi. It is a function of g1, g2, g3, and t, and this g1, g2, g3 are itself the function of space coordinate x comma y comma z comma t. So therefore this quantity phi will be the function of the space coordinate x comma y comma z comma t. So equation 8, this describe this phi in the Eularian description. So a quantity phi is given in the Lagrangian description. We find out the quantity phi in the Eularian description. Now we shall discuss if a quantity is given in the Eularian description, how we shall describe the same quantity in the Lagrangian description. So suppose psi be a quantity in the Eularian description. So in Eularian description psi is given, so psi must be the function of the space coordinate x comma y comma z and time t. Now suppose u comma v comma w with the components of velocity at this point x comma y comma z comma t at time t. Then we know that in the Lagrangian description, this u comma v comma w is expressed as u is equal to dx by dt, v is equal to dy by dt, and w is equal to dz by dt. And so we can write this one, u is equal to, this one will be the dx by dt, and this one will is some function of x comma y comma z comma t. Okay, because this is in the spatial description. So dy by dt is equal to g2 x comma y comma z comma t, and dz by dt is equal to g3 x comma y comma z comma t. Okay, so we taken from this equation, this equation number 4, because velocity components are given by g1, g2, g3, and dx, u, v, w are dx by dt, dy by dt, and dz by dt in the Lagrangian description. Now this equation 10, this is the system of simultaneous system of equation. This is a system of first order equation. So there are three first order systems. So when we shall solve this equation 10, then for x, y, and z, and then we shall get x, y, z, x, y, z. The solution of this system will involve the three arbitrary constants c1, c2, c3, and these three arbitrary constants will be obtained with the help of three initial conditions. Those are x is equal to x naught, y is equal to y naught, z is equal to z naught at time t. So when we shall solve this equation 10, then we shall get x, y, z will the function of x naught comma y naught comma z naught and time t. So we have solving equation 10 and using the initial condition, we get x is equal to some function f1 of x naught comma y naught comma z naught comma t, y is equal to some function f2 of x naught comma y naught comma z naught comma t, and z is equal to some function f3 of x naught comma y naught comma z naught comma t. Now we shall use this equation 11. So we shall use this equation 11 into equation 9, when we shall get then we shall get psi is equal to psi is a function of f1 comma f2 comma f3 comma t, and these f1, f2, and f3 are itself the function of x naught comma y naught comma z naught and time t. Its meaning is that the psi will be the function of x naught comma y naught comma z naught and t. So this equation 12 describe this psi in the Lagrangian description, because it is a function of the initial coordinate x naught, y naught, z naught and time t. Okay, so we discuss how to describe the motion, and we have tried to establish the interrelation between both the descriptions. Now let us see one example based on these descriptions. So suppose for a two-dimensional flow, the velocity component at a point in a fluid may be expressed in the Eularian description by u is equal to x plus y plus 2t, v is equal to 2y plus t. We have to determine the Lagrange coordinate as a function of initial position x naught and y naught at the time t. Okay, so here the motion is given in the Eularian description. We have to be determine the same motion in the Lagrangian description. So it is given, how we shall solve it. It is given in Eularian description, u is equal to x plus y plus 2t, v is equal to 2y plus t. Now since in Lagrangian description u we are expressing as dx by dt, we are expressing as dy by dt. So we shall use equation 14 to the equation 13. We shall get a system of equation. So dx by dt is equal to x plus y plus 2t, dy by dt is equal to 2y plus t. So this is the system of two first order equations. This is a simultaneous system. So firstly we shall solve the second equation, and we shall obtain y, and thereafter we shall put the value of y in the first equation, and we shall solve for the x, and then we shall get the x and y, and this solution will involve two arbitrary constants, and those constants will be obtained with the initial conditions x is equal to x naught, y is equal to y naught at t is equal to t naught, which is equal to 0. Now let us see how to solve this equation. Dy by dt is equal to 2y plus t. You can write this equation as dy by dt minus 2y is equal to t. So we are written dy by dt minus 2y is equal to t. Now integrating factor is e to the power minus 2t. So y into e to the power minus 2t is equal to integral t e to the power minus 2t dt plus c, where this c is a constant of integration. Now I multiplied the whole equation by e to the power 2t. So e to the power 2t into e to the power minus 2t is 1. So I will get y is equal to e to the power 2t integral t into e to the power minus 2t dt plus c e to the power 2t. So now we shall solve this integral by integration by parts. So y is equal to e to the power 2t. Now this t you assume as a function, first function, and e to the power minus 2t you assume as a second function. So first function into integral of second, so that is t into e to the power minus 2t by minus 2 minus integral differentiation of first, so that is differentiation of t is 1, and again integral of e to the power minus 2t. So integral of e to the power minus 2t is e to the power minus 2t by minus 2, and which one will be once again integrated, so you will get e to the power minus 2t by minus 2 whole square plus c e to the power 2t. So now we shall simplify it. When we shall simplify it, we shall get y is equal to c e to the power 2t minus 1 by 4 2t plus 1. So we find out y here. Now this value of y we shall put in this equation here. So this equation, first equation, you can write as dx by dt minus x is equal to 2t plus y. So y value put it. So y is equal to c e to the power 2t minus 1 by 4 2t plus 1. So this is the equation now. Now we shall solve this equation for x. So here integrating factor is g to the power minus t. So x into e to the power minus t is equal to c e to the power minus 2t into minus e to the power minus t. So we shall get c e to the power t, and integration of c e to the power t is c e to the power t. So this one plus 1 by 4. Now here you have multiplied this one e to the power minus t. So again you do integration by part, then you will get 6t minus 1 divided by minus 1 e to the power minus t minus 6 by 4 e to the power minus t minus 1 whole square plus d, which is a constant of integration we added. So now whole equation I multiplied by e to the power t, then I will get x is equal to this term I am writing first. So d e to the power t plus c e to the power 2t minus 1 by 4 6t minus 1 minus 6 by 4, and on simplification it will give x is equal to d e to the power t plus c e to the power 2t minus 1 by 4 6t plus 5. So we find out x and we also find out y. So this involves two arbitrary constants c and d, which will be calculated with determined with the help of initial condition. That condition is x is equal to x naught, y is equal to y naught, and t is equal to t naught, and for simplicity I consider t naught is equal to 0. So when we shall use this initial condition to the first equation, that is solution for y, then I will get y naught is equal to c minus 1 by 4. So c is equal to y naught plus 1 by 4, and when we shall use this initial condition to the second solution, that is the solution for x, it will give x naught is equal to d plus c minus 5 by 4. So that is d is equal to x naught minus c plus 5 by 4, and c value you put from here, that is y naught plus 1 by 4. So we shall get x naught minus y naught minus 1 by 4 plus 5 by 4. So when we shall simplify, d we shall get as x naught minus y naught plus 1. So c we got as y naught plus 1 by 4, and d we got as x naught minus y naught plus 1. Now this c and d values we shall put in the equation, that is the solution for x and solution for y. So we shall get x is equal to x naught minus y naught plus 1 e to the power t, that is this equation here I am putting. So d value here you put, c value here you put. So we shall get x naught minus y naught plus 1 e to the power t plus y naught plus 1 by 4 e to the power 2t minus 1 by 4 6t plus 5, and this one I am assuming this is the function of x naught y naught and t, because it involves x naught y initial position x naught y naught and time t. Same way we shall put the value of c here in this equation. So when we shall put, then we shall get y is equal to y naught plus 1 by 4 e to the power 2t minus 1 by 4 2t plus 1. So this is also a function of x naught y naught and t. So x and y both are the function of x naught y naught and t. So this equation represents the motion in the Lagrangian description. So in this problem, the motion is given in the Eularian description. We find out the motion in the Lagrangian description. So these are the coordinates in the Lagrangian description. Now we shall discuss one more example here. So I am giving this one you for exercise. So you please try as exercise. Exactly similar problem as we discussed previous one. So velocity components for two-dimensional flow system can be given in the Eulerian system by u is equal to 2x plus 2y plus 3t and v is equal to x plus y plus t by 2. Find the displacement of the fluid particle in the Lagrangian description. So exactly similar problem. So this is an exercise for you. You please try it. And in the next class, we are going to discuss the velocity and acceleration of fluid particle. We shall find the acceleration in orthogonal curvilinear coordinate system. That is, we shall try to find out the acceleration in Cartesian as well as cylindrical and spherical coordinate systems. And we shall define the material, local and convective derivative, and we shall establish an interrelation between them. So thank you very much. Thank you very much for attending the class.